All right, now we get to talk about quantum mechanics. Um, so Max Planck was studying black body radiation, and we sort of touched on black body a little bit, radiation a bit this semester, that the heat, or the rate at which heat radiates from a body is proportional to this Boltzmann constant times its emissivity times the area times the temperature to the fourth power. And so Planck was trying to make sense of all of this black body radiation and all the data on black body radiation. And what he decided was that you needed to think of these molecules as little bitty oscillators. It's almost like, so suppose we had our little oscillators we did early in the semester, just a mass on a spring, right? Except you only got to pull the spring to discrete positions before letting it go, right? So it had its default oscillation it could do, and then you could pull it one level and it would oscillate there, or you could pull it two levels and it would oscillate there, or you could pull it three, and so on, right? So what he found was this really startling result that you couldn't pull the spring just anywhere you wanted. And in fact, the relationship between the fundamental oscillating frequency, the fundamental oscillation energy, which is just 1/2 HF, and these levels was that you could only change by integer numbers of HF, right? So if you don't do anything, right? If you don't do anything, then here's your world. The atoms, the molecules are oscillating. They're acting like little oscillators at a particular frequency, and the total energy in the oscillation is 1/2 HF. And H is this constant Planck came up with, which is, see 10 to the minus 34. This is kind of small. So this is the oscillation energy of an individual molecule. All right, so then he discovers the change between them, the first state, or the ground state, and each additional state is just an integer multiplier times HF. And that's expressed here by the radiation can either be emitted or absorbed in energy aliquots of delta E equals HF. So this very startling result, energy is quantized. It doesn't come in whatever you want in terms of the amount, it's quantized. If we look at the emission spectrum of oxygen, you see all these lines, right, that are due to discrete state changes in oxygen. This is exactly what he was looking at some level, that we can analyze these spectra and we can see what the delta E is for different parts of different states of oxygen. All right. Following on the heels of this was the photoelectric effect. In the photoelectric effect, you shine light on, you set things up so that you got a cathode, all right, you got some cathode and you've got some anode, you got a battery here, so that you've got a voltage between them, right? And then you let a light shine down on here. And what happens is nothing, depending on the frequency of the light, right? So nothing happens at all until you hit some threshold frequency. And beyond that frequency, electrons start popping off and heading over to the anode. All right? And you can even once you go up above that frequency, right, you can even turn the battery around. Turn the battery around so that electrons would want to go the other way, and you can shine a light on here and you will get some electrons going that way. All right, if you're high enough above the threshold frequency where things started moving. So what does all of this mean? All right, Einstein was one of the ones that helped make sense of all this, and so here's what they found. You can vary the frequency, and up until you hit that threshold frequency, no electrons move, no effect whatsoever, right? And then once you get to that, once you get past that threshold, all right, you begin to get electrons. All right, that's step one. Step two, all right, once electromagnetic radiation falls on the material, electrons are ejected without delay. That means it doesn't take a while for them to build up to the point where they take off. It's not like you're winding up a spring and eventually it's going to go. It's not like you're bumping them up a little bit at a time. Boom, you hit them with a photon and off they go. All right, there's no sort of slow process. It's not like charging a capacitor before it fires, nothing like that. Just wham, they're gone. All right, then the number of electrons ejected depends only on the intensity, not the frequency. So once you get above the threshold frequency, right? Once you get above the threshold frequency, you start getting electrons. But the number you get depends only on the intensity. All right, so you double the wavelength. You double the frequency. Cut the wavelength in half. You got a much more energetic photon at this point, but you don't get more electrons. You just get faster electrons. So if you want more electrons, you have to increase the intensity. All right. We can, by varying the intensity, measure the maximum kinetic energy. All right, maximum kinetic energy is independent of the intensity. So it doesn't matter how bright the light is, all of them come off with the same energy. All that matters is the frequency. The frequency completely determines the kinetic energy of the electrons that come off of the cathode or anode, depending on which one you're illuminating. All right. Finally, this threshold frequency is in fact due to a binding energy of the electron to whatever material we're kicking it out of. So the electron is bound to the material. If it wasn't bound to the material, they just take off on their own all the time anyway, right? So the electron is bound to the material. The threshold frequency tells you, right? The threshold's frequency tells you what that binding energy is, right? Because at that binding energy, the kinetic energy they have is 0. So HF at the threshold, right? HF at threshold is the binding energy. HF at threshold is the binding energy. And then as you go above that threshold frequency, all you do is add to the energy of the individual electron that you're kicking out of the material. So all that makes sense? Does it sound good? All right, so this is the photoelectric effect. And we'll start up with this next slide in the next lecture.